4, okay? And this is basically Edwin's solution. Okay. Combi. Okay, so the question asks you, so Ivan invites 2 N guests. Okay. And he has N white hats. And can you see this? N black hats. Okay, this is the way we do this. So N white and N black hats. And what he wants to do is he wants to give them each a color, each a hat. So and then forms dance groups, okay? Dance circles. Does that make sense? Yeah, so if so Edwin manages to get 1, 4, and 6, it'll be a very good result. So
that's 23.
Which maybe we can talk about more next week. Okay, so forms dance circles, okay? And what's a dance circle? Well, it has to be these people. They have to have white and black sort of alternating colors, yeah? Okay, and there could be a couple of dance circles. They have to have at least 2 people in them, yeah? Okay, and I guess you can sort of see it has to be even, yeah? So the question is, show that there are 2n factorial different ways to prove of forming circles, yeah? I don't know, there seems to be something, like a theme with this test, that the question wording is always a little bit awkward, yeah? Like, when you look at this question, it makes you think that you're forming just the circles, you don't care about the distribution of the hats, right? But what they mean is, you can tell what they mean by doing the examples, because not all of them will be 2n factorial, right? So, if you have like 4 people, so they say the people are distinct and the hats are not, okay?
The people are distinct. Yes.
So maybe we can call them 1, 2, 3, 4, right? Yeah. You can basically put them all in a circle, right? Yeah. Or you can have 2 circles, right?
Yeah, and they all have different orders.
Okay. And
wait,
so
like do rotations of circles count, or like reflections of circles?
So yeah, look, so the orientation matters, yeah. So if you knew that if the colors were already fixed, yeah. So these 2 people basically have to be paired up, or they can switch once, yeah. So there's 2 ways, yeah. And if the colors are fixed here, basically all they can do is switch 2 of them, yeah. So there's 2, yeah. So it's 4 and not 4 factorial, yeah.
Yeah.
So that's why you have to also account for the ways of assigning hat colors.
Oh.
Yeah.
Ah, I see.
Does that make sense? So.
But that's like.
So if you're assigning hat colors, then this becomes 3 factorial ways of getting the people in there, right?
Mm-hmm.
And then you're timesing it by 2 ways of assigning the colors, yeah. And here there's like, there's so basically you're choosing two teams of 2 out of 4 people, right?
Yeah.
So that's 4 choose 2 over 2, so it's 3, yeah?
Yeah.
And then you can choose the colors in 2 different ways for each one, yeah? So it should be times 4, is that right? So that's 12 and 12, yeah? 24 is 4 factorial, yeah?
No, 19. Oh, yes. Yeah.
Okay. So you have to take some time to interpret the problem, okay? So I want to go through Edwin's solution, and I think it's pretty good. And if I do go through some solutions, there are places where I'm not like focused on, but may lose some marks because of lack of care with expressions, yeah? Okay, so it's not just forms dancing circles, it's actually forms colored dancing circles, right?
Yeah.
Colored. And I'll write colored in black. Oops. Okay, so the first thing is, I think this observation. Also, yeah, I think Singh got quite far in this problem too. So they both had this initial step. So basically, there's 2n, choose n ways of picking the hat colors. Yeah.
Mm-hmm.
So there's 2n people, and you are give n of them white hats, and therefore we have to give the other n black hats, right? So that's 2n factorial. So that's the answer that you wanted, right? Over n factorial times n factorial, right? Or n factorial squared. Okay. So it suffices to basically show that
The way to the sign.
yeah, the dance circles after the coloring, yeah. So it suffices to show dance circles is this is like paraphrase to the max, yeah.
Yeah.
Okay. And for it to suffice to show that, right? It basically means that the dance circles only depend on the like no matter how you assign the colors of the hats, the number of dance circles have to stay the same, yeah? And then it's just this times that, right?
Yeah.
Okay. But no matter how you assign the hats, the dance circles are the same, right? The dance circles only depend on the colors of the people basically and knowing that they're different. Yeah? Okay. Yeah, I guess one thing is they need to translate the questions into English, so it's not just trivial for them, and it's okay. So we need to show the dance circle is n factorial, right? Okay, so then so you suppose you have so you have the black hats B1, B2, B3. So I'm following Edwin's solution, yeah. B N, and then the white hats are white 1, white 2, white 3, white N, yeah. Okay. So the way it goes is there's one way to place the first B1, yeah.
Mm-hmm.
So you could just place him. He's in a circle, right? So he's in a circle, yeah. So he's B1 in here, yeah. Okay. So there's 2 ways to place the B2, okay. So the B2 can either start his own circle, yeah. So like 2 ways relative to the B1, yeah. And it doesn't matter. Like so it can either start its own circle, right?
Or it joins B1.
So it can either be basically they're separate or they're not separate, right?
Yeah.
Okay. Yeah, and so I guess you have to have the understanding that we're putting the black colors in first, and then we're putting the white colors in. Yeah. So we're not worried at the moment that they don't form legitimate circles. Okay. So Okay. Okay, so it starts getting a little bit complicated, but it still remains the same pattern. There's three choices for B3, okay? So to think about that, okay, so
Aren't they kind of full? Because like, if B1 and B2 are together, you can join them.
Yeah.
Or be separate.
Yeah.
And if they're separate, wait, no, there are 5.
No, but they don't coexist. Yeah. So if B1 and B2 are together, they can't be separate, right?
Oh.
Yeah. So you just have to check if B1 and B2 are together, right?
Are there 3 for both?
Yeah. That's what you have to check. Yeah.
Aren't there 2 if they're together?
Oh no, if they're together, there's 2, but you could also create a new circle. Yeah, so maybe I can explain this. So Edwin explains this one actually as well. So look at this, okay? So there's 2 cases. There's the B1 and B2 are together, yeah? And there's other cases they're separate, yeah? Yeah. So in the first case, you can put the B3 like here, which is one circle, yeah? Or you can put it here, right? There's another circle. Or you could create a new circle, yeah? So relative to B1 and B2, they could be here and here or not in the same circle, yeah? Okay. If they're separate, then you can either be with B1, be with B2, or neither, yeah? Okay. You see that? Okay, so there's 3. Okay. I wish I wrote B4 there. This looks planned. Okay, so with B4, okay, it seems to be a lot of cases now, right? So they could have been together, okay? They could have been all separate. They could have had like 3 and 1, yeah? You could have had 2 and 1, yeah? Okay. I guess to kind of make all the cases combined, we're still trying to show it's 4, okay? Okay, so all those cases, right? But you notice no matter how you actually break up these things into circles, okay, there's always going to be 3 people, okay?
Yeah.
And your choice essentially comes to like, which person do you want to be the left of, okay?
Yeah.
So
if any.
Yeah, so basically like, yeah, so there's sort of, if you want to be on the left of someone, there's 3 ways, right?
Yeah. Or you can choose.
And if you want to be on your own circle, there's one way, yeah? So the whole idea is because this number of people is fixed, so the number of positions you can choose is fixed no matter how many different circles they happen to be on, yeah? Does that make sense? So you can kind of imagine there being dividers or there not being dividers, right? But you can always sort of put your B4 on either the left of B1, yeah? And that might put them on the same circle even, yeah? Yeah? Or it could be on the left of B2, yeah? So if they were on the same circle, they'd be on the other orientation, right? They'd be on the... Sorry, I'm saying left when I'm writing it on the right. Okay, but it means the same thing, yeah? Or you can put it here, or you can put it just separate, yeah?
Okay, so that makes n factorial entirely.
Yeah. So that actually makes n factorial, right? So he actually wrote an induction, but so this is n, right? Then you have n factorial. Where is it picking the places, yeah? Okay, and then then now you have to insert the white ones now, yeah? Okay. But notice you have to insert the white ones next to the black ones, yeah? So if you're kind of good with this idea that there's like one place to the left of all the black ones, yeah, you basically have to put like W1 to the left, to the right of the B1, right? Unless you can permute them. Yeah?
Oh.
Does that make sense? So like every space has to be filled by a white one, right?
Mm-hmm.
So the spaces are forced.
Yeah.
It's just which permutation of them you put them in, right?
Yeah. I just thought about it like you put W1 in like n spots, right? Because
Yeah.
N spots. And then W2 is n minus 1.
Yeah.
So it's like one's taken.
Yeah, it's basically the same as this but backwards, right?
Yeah.
So you have n minus 1, yeah?
Mm-hmm.
And then all the way up to 1, yeah?
Oh, so that.
And that gives you n factorial.
Oh.
And it's n factorial squared, okay? So, if you're reviewing this kind of problem, how could you understand it more? Well, you might want to relate it to something that you already know about. Okay, so in my case, it would be this group theory thing, okay, which I sort of talked to you about before. And I'll remind you of it in a little bit. But in your case, which kind of it will lead to the same kind of thing, is like you're basically trying to show that this kind of arrangement is equal to this number, right? So you're kind of trying to see like if you can maybe make a bijection. Like, was there another way you could see like? So this is sort of this is like ingenuity, right? Because you're kind of just showing two new things that are equal in this way, yeah.
Mm-hmm.
So ingenuity is definitely what we need in these competitions. But if you wanted to go by theory, right, it would be kind of like recognize this is equal to some well-known thing, which is known, what the counting number is known, right? And then show it's equal to that thing, right?
Mm-hmm.
Okay, so in this case...
that's the same as just ordering 2n.
Yeah. So can you see that, like, basically this amounts to... so it's basically this process that's important, right? I mean, that's really the main thing here, yeah? This part is kind of well understood, yeah?
Yeah.
So, basically, I guess the question I want to ask and answer is it obvious that dance circles... So basically, it's like if you remove all the coloring and all this other fluff, right? It amounts to forming dance circles, right? Okay, without any restrictions. So they don't have to be two or more, right? See, the problem is when there's two, they have to be even, yeah?
Yeah.
Let's just forget about that. We just have the black hats, right? They're just forming dance circles without any restriction. Okay?
Yeah.
And you're trying to relate the forming of dance circles with n people to the number n factorial. Yeah?
Mm-hmm.
Okay, and this is a well-known fact in group theory that I sort of touched upon at some point before, okay? So I want to explain it like this. So do you remember this thing called the symmetric group? So sometimes SN, or sometimes it's called symmetric N. Yeah? Symmetric group on N. Yeah? It's basically all the permutations of N, yeah? So another way of saying that is a function from N elements to itself, yeah? Which is invertible, it's bijection, yeah?
Oh.
Yeah? So this set has n factorial things. Yeah? So this is like you know, you might not instantly know it, but you could remember it because it's in your theory, yeah? There's n factorial, there's n ways to send the first one, n minus 1 to send 2, right? So this is the size n factorial. Okay? And there's a well-known fact that every permutation, okay, can be expressed in cycle notation. Okay? So what does that mean? Okay, so let's take a permutation. So like let's say we have like 1 goes to like, let's say n is equal to like 8, yeah? So 1 goes to like 7, yeah? 2 goes to like 6, 3 goes to like 8, yeah? 4 goes to 1, yeah? As long as they're different, it's going to be a bijection, yeah? 5 goes to 2. I'm just randomly writing numbers, yeah? It's my job description.
Yes.
I just randomly write numbers. Okay. 7. Okay, you're probably losing sight of the board here. Goes to 5, okay. And then something goes to 4, yeah? So 8 goes to 4. So 8 goes to 4. Yeah? Okay. So basically what cycle notation is, okay? And it's a little bit different if you're doing left or right cycle notation, but let's just not worry about that, okay? You start at 1, yeah? So you go 1, yeah? Where does it go to? It goes to 7, yeah? Where does 7 go to? It goes to 5, yeah? See? 5 goes to 2, yeah? And then 2 goes to 6. Where does 6 goes to? 6 goes to 3. Okay, this is not a good example. 3 goes to 8. Okay. 8 goes to 4. 4 goes to 1. Okay, so that's a whole cycle. Okay. So it wasn't the greatest example, but what I'm trying to say is this corresponds to the dance group of everyone in this order. Yeah. So basically, if you form the dance group, this is B1, B7, B5, B2, B6, B3, B8, B4. Yeah. And it doesn't matter. The cycling doesn't matter, right? Because this is the same as if you put 4 at the front.
Yeah.
And then put 1 next, right? Because 4 goes to 1. Yeah?
Sure.
Yeah, we definitely did this in our class, but who was in that class at the time? That seems to be changing all the time. Okay, so let's take another example. So what if we had like, take some random example, like 1, 2, 3, 1, 4. Say some numbers.
Yeah.
8. Okay, I'll take 8. 6.
That doesn't matter.
You can take whatever number you want.
Does 6 go to 6? What?
Yeah, it has to, right?
Oh.
This is you're not trying to make it convenient. You're trying to make it break, okay?
Okay.
All right. So what's next?
5.
5, yeah. Yeah.
7.
7, okay. So can you see here? 1 goes to 2, yeah.
Yeah. If it goes to itself, then it's like a different group.
It's his own dance group.
Yeah.
So you're allowed to have 1, right?
Mm-hmm.
So 1 goes to 2. 2 goes to 3.
Oh, the other one was.
3 goes to 1, yeah.
The full thing. Oh, yeah.
So it loops. Okay. It has no choice. It either gets everything or it stops, right?
And if it stops, you just take another one.
Yeah.
And then 4 goes to itself, so it's by itself.
Yeah. So where's 4?
4 goes to 4.
4 goes to 4, yeah.
Yeah.
5. So you usually don't write that, but we're doing it for our. 5 goes to 8, yeah.
Mm-hmm.
And then 8 goes to 7. 7 goes to 5. So that's a cycle, yeah.
Yeah, and then 6.
6 goes to 6.
Ah, that makes sense.
Yeah.
Yeah.
Yeah. So you guys are onto it now. So basically, so this is a dance group with B1, B2, B3. That's B4 and another dance group. Yeah. And then you have to insert the white ones, in factorial. So this tells you a lot of things. This is a very fundamental fact about the symmetric group. It says it's generated by cycles. See? So if you want to look at the generators, you can kind of just consider how to get the cycles. Okay. So it's a very well-known fact. Basically, it's like if you want to achieve any permutation, you kind of just need a big cycle and like a transposition or something. Okay? Or you just need transpositions. That's another result. Because obviously you can permute everyone by just swapping two people until you get it, right?
Yeah.
So okay, so what is this claiming? This is a bijection between the symmetric group. So this is like a dance group, right?
Mm-hmm.
With a set of dance groups. Is in bijection with the number of like symmetric group. Yeah, in cycle notation. Yeah. It's strange because I thought this would have been the solution that they gave, but I couldn't even understand what the solution said. Anytime the solution has a sum, I just kind of tend to not read it. So I didn't know what the official solution really said.
Sigma dash. Yes.
Okay, so yeah, so remember I was trying to use this as an example of kind of if we can solve the question, okay, and then review it in a way that makes us sort of understand the question, you know? So in a sense, it's like, how can we know how to solve the question? That's step one. But how can we make that process routine? Yeah, like is it really just a consequence of something we already know, right? That's kind of what routine means. Or is it really something unknown and we have to really try hard to relate it back? Okay. I mean, in essence, the proof that was given before with the dance cycle is proving that this is, they're in bijection, right? Okay. I guess the difference between saying that they're in bijection and this is you're specifying what the bijection is, and in a sense, it's a natural bijection. Yeah.
Yeah.
Okay. So this is sort of more the culture and style of maths these days. Okay. Like I'm sure back in the old days, it's just like okay, these two sets have the same size. We're good. Yeah.
They seem similar.
But now we look for functions that relate the sets. Yeah. Okay, I'll stop talking about that.